Hello, mathematicians. I wanted to talk to you about graphing a transformed trig function. So if you've looked at the old practice tests that I've posted, you'll have seen that there's a problem, which is graph a complete period and find the amplitude, period, phase shift, and vertical shift of, in the practice um, test, it was this problem. And I wanted to talk through this and walk through it because this is beyond the scope of what you've seen on Web of Science. So you might need to do a little bit more practice. So I'm going to do a slightly modified version. I'm going to do that. So to start this, it's going to be helpful to have the generalized trig function equation, which is a times sine of k times x minus b plus h. And it could either be sine or cosine, either way. The absolute value of a is what's called the amplitude, which is half the height of the graph. The height of half the height of the regular sine cosine functions is 1. To figure out the period of one of these, which is how long it takes for it to repeat, we need to do 2 pi divided by k. H is the vertical shift. And b is the phase shift. So if you remember your transformations, modifying the input by adding or subtracting something moves the graph left or right, but in trig world, we call that a phase shift rather than a horizontal shift. And adding something or subtracting something outside of the function moves the graph up or down, which is a vertical shift. Okay, so for our example here, we have the absolute value of 3/4 is going to be our amplitude. Since that's less than 1, it tells us that the graph of this should be a little bit more scrunched or shorter than the graph of the regular sine or cosine functions. In order to find the k, what we need to do is factor what's inside our parentheses here so that there is, if you'll note, in the generalized function here, there is a 1 there and a number in front of parentheses in front of the x. So we need to factor our 2x plus 2 pi over 3 and pull out the thing that's in front of the x. So pull out a 2. So x plus pi over 3. And we also need this to be a negative in there. So this is the same as 2 times x minus negative pi over 3. So our k is going to be 2. So our period is going to be 2 pi divided by 2, or pi. The period of the regular sine and cosine function is 2 pi, so this is going to be repeating or scrunched up and repeat faster than the regular sine or cosine function. And our horizontal shift, in this case, is 1 plus 1, so this is going to tell us the graph has moved up 1, and our phase shift is negative pi over 3. Let me briefly talk about the sign switch that's going on here. So our phase shift is negative pi over 3, but if you'll note, there's actually a positive pi over 3. If you remember your transformations, adding something to the input of a function moves the graph left. Well, negative numbers are to the left on our number line. That matches why this is negative, right? The addition inside the input to the function matches the transformations that you would go over in algebra class. And the fact that this is a negative pi over 3 phase shift means our graph is going to be starting to the left of where the normal sine or cosine function graph would normally start. Okay, so to go through the graphing process here, what we need to do is take our phase shift, and I'm going to write 5 different lines starting off with my phase shift. And I'm writing 5 different lines, but effectively what we're going to do is build 5 different points, x and y coordinates, to plop on a graph and then play connect the dots. So what I want to do after writing down my phase shift is take my period, which is pi, and add quarters of my period to the phase shift. This is going to be a little bit of work here because I have to find a common denominator. There should be a pattern in the answers I'm getting. Note that, let's see, let me convert this one into twelfths. 4 over 4, so this is negative 4 pi over 12. So if you look at these, you note that there's a pattern. It's increasing by 3 pi over 12. So there should be patterns all the way through doing this entire process. And if they're not, that kind of is a hint that you've messed up the arithmetic somewhere. Cool. All right, so we got these. These are our x values, or inputs, that we're going to input into our trig function. Let me go ahead and copy this and oops. Okay, so now what we want to do is I want to take these values and we want to input them into our function. So what we want to do is input these where the input goes. And you could either use the original version of the equation or the factored form. Either way will be fine. So I'll just use the original. I'm going to go ahead and get a common denominator here. And actually what I think I'm going to do is I'm going to take this all the way down to a new line. So I have a little bit more room to write. Okay. Oh, should be a plus 1. All right, I'm just going to leave that for now. And let's continue with the second point, negative pi over 12. One thing I'm going to do here is be a little bit clever. I noticed that over here I'm going to be in twelfths, and here I'm in thirds, but I already found the common denominator for the 2 pi over 3 up here. So I'm going to skip that, and now write 8 pi over 12 just to save myself a little bit of time. There should be a plus 1. Okay, let's do the next one. 2 pi over 12. Next one, 5 pi over 12. And then the last one, 8 pi over 12. Okay, again, note that there should be a pattern all the way through the whole process. These are going up by pi over 2. So now let's simplify our final trig functions here. Cosine of 0 is 1. So we get 3/4 times 1 plus 1. That's 3/4 plus 1. I'm going to write this as a decimal, even though I don't usually like writing things as decimals, because I have to put these on a number line, right, when we graph these, or on the coordinate axes. Cosine of pi over 2 is 1. No, sorry, cosine of pi over 2 is 0. Cosine of pi is -1. Cosine of 3 pi over 2 is 0. Cosine of 2 pi is 1. And again, note there should be kind of a pattern all the way through this process, and there is. These are nice, relatively nice numbers to plop on a graph. Okay, so let me also talk about a couple other points here. Let's take a brief look at this guy, and this guy, and this guy. And note, I didn't reduce those. And maybe let's see, 8 pi over 12 divide top and bottom by 4, we get 2 pi over 3. Might have actually been wiser to reduce those, because then I would have had a common denominator with the thirds that were in here. Okay. Depending on the problem you have, sometimes you will not want to reduce those, because sometimes you would lose the common denominator with the b. So just make sure you pay attention to that. Okay, so now what I want to do is collect all this information. These guys are, that I circled in red over here, are the output or y values. And then we're going to plop these on a graph. -4 pi over 12, negative pi over 12. Two pi over 12, 5 pi over 12. Let me guess, 8 pi over 12. Yeah, good. Okay, and then we have 1.751, 0.251, and 1.75. And note, in this case, I specifically did not reduce this, or this. Let me talk about why as we go through graphing this here. So now we are ready to graph this. So my tick marks that I need to put on the horizontal axis are evenly spaced by twelfths, 3/12 in particular. But let me go ahead and just plop twelfths on here. Again, as long as they're evenly spaced, the exact measurement of how long they are doesn't really matter. And then 1 pi over 12, 2 pi over 12, 3 pi over 12, 4 pi, 5 pi, 6 pi, 7 pi, 8 pi. So let's see here. Okay, the reason why I didn't reduce those three that I have bracketed on the left is if I had and gotten pi over 6 or negative 2 pi over 3, or negative pi over 3, or 2 pi over 3, then I would lose my common denominator. And since the tick marks have to be evenly spaced, and when my x values are not reduced, it's a little bit clearer that they're all denominated by twelfths, right? So if I reduce them, it's harder for my brain to kind of relate, well, where is pi over 6 in relation between negative pi over 12 and 5 pi over 12? Or where is negative pi over 3 in relation to negative pi over 12? Well, I don't know, right? But if they're all the same denominator, that might make it a little bit easier to kind of envision how to plop them on the number line, right? Like we have 2 pi over 12, 1 pi over 12, 0 pi over 12, negative 1 pi over 12, negative 2 pi over 12, negative 3 pi over 12, negative 4 pi over 12, right? That's just multiples. Those are of 1/12 of a pi, all equally spaced out on the number line. So that's why I didn't reduce those there. So now what we want to go do is plop some markings on our vertical axis here. Say that this is going to be 1. I need a little bit more room. One, 2. Okay, and then let's plop some coordinates on here. Negative 4 pi over 12 is at 1.75. Negative pi over 12 is at 1. Negative 2 pi over 12 is at 0.25. 5 pi over 12 is back up to 1. And 8 pi over 12 is back up at 0.75. So now we want to play connect the dots. So this thing is going to do something like this. And it's going to repeat. And now we have graphed one complete period between here and here. So what I want to do for comparison purposes is I want to label the regular sine function on here. Draw and label the regular sine function. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. This should be 24 pi over 12 or 2 pi. Or, we want to draw the regular cosine function on here because we want to compare what we've got to a regular cosine function because this was a cosine function. So let's see, 9, 10, 11, 12. So this comparison part that I'm doing is not really something you have to be able to do for the test. But this is just kind of for informational purposes. So let's see, cosine of 0 is, angle 0 is 1. Cosine of pi over 2 is, wow, it'd be great if I put the dot in the correct place. Cosine of angle 0 is 1. Cosine of pi over 2 is 0. Cosine of pi is negative 1. Cosine of 3 pi over 2 is 0. And cosine of 2 pi is positive 1. So the regular cosine function does something like this. So let's compare and contrast these with what we had said at the very beginning about the amplitude, period, and phase shift. Our amplitude is 3/4. So that means that this thing should be from the center line of its graph to the top and the bottom of it, a little bit skinnier than the a little bit shorter than our green graph. I didn't draw it exactly well enough for that maybe to be apparent. I'm sorry. The period of our graph is pi, which means it repeats quicker. That definitely seems to be true. This guy, the regular cosine function, takes that long to repeat. Our red function took just this long to repeat. So that jives with what we've got. We had a vertical shift of up 1. That looks right. And we had a phase shift of negative what was our phase shift? Our phase shift was negative pi over 3, which looks right. Our graph started over at negative 4 pi over 12. So all that information that we ascertained by using this up here jived with what our graph got. So that means I don't think we screwed anything up. Yay, that's good. Okay, so what I'm looking for you to be able to go through and do is basically this whole process. I'll just summarize it here really quick. You want to find the amplitude, period, phase shift. You might have to factor to find the correct period and factor the input to find the correct period and the phase shift. Then you want to take the phase shift, write 5 different lines, and then take quarters of the period, add it to the phase shift. You might have to find some common denominators and then plug them in. And yes, I'm looking for you to show most of your work for this by hand. It's excellent demonstration that you have your fraction manipulations and unit circle stuff down really well, which is what you're going to need for the latter half of the class and for calculus. All right, guys, that is it, and I hope you have a wonderful day.